everyone. So today we are going to see the subtopic that is laser metrology. So today we are going to see all these contents, that is basic concepts of laser, advantages of laser, techniques of laser system, laser interferometers, types of laser interferometers, and the applications of laser interferometers. So let us see first the basic concepts, that is the basic concept of laser. Laser it stands for light amplification by stimulated emission of a radiation. A laser instrument is a device, okay, which used to produce powerful monochromatic collimated beam of light, okay, in which the waves are consistent and the coherent, okay, and the laser development is for production of clear coherent light, okay, and the advantage of this coherent light is that the whole of the energy appears, okay, whatever the energy is there, it appears to be dissipating from a very small point, okay, so it dissipates the energy, that it appears that the whole of the energy is that from a very small point, okay, it goes through a very small point, and the beam which can be focused easily into either a parallel beam or onto a very small point by the use of lenses. And a major impact on optical measurement has been made by development in electro optics by providing automation, and along with that it is having a faster response time, okay, and the radiation sources have developed in a number of areas. The most important development are light emitting diodes and lasers, and the laser is used extensively for interferometry, particularly the helium neon, that is HENE gas type. The laser distance measuring interferometer has become an industry standard, okay, and this produces 1 to 2 diameter beam of red light power of 1 megawatt and focused at a point of very high intensity. The beam begins to expand at a rate of 1 per meter. The laser beam is visible and it can be observed easily, and this is used for very accurate measurements of the order of zero point 0.1 meter each 100 meter, okay, this is what the accurate measurement. Now next, that is, sorry, it is one mistake. So here we are going to see the advantages of laser, okay. So first, that is, it is light and easy to use equipment, okay, and it is having a shorter time for preparation and measurements, okay, and next, that is, it is possible to measure and align at long distance with greater accuracy. This is what happens with the laser. And the next, that was the, it is possible to measure the directions, both directions, either x and y or x and z, at the same time, okay. So due to that, what happens, it saves the time, okay. And the next point, that is, the reference of the laser beam is always 100% straight, okay. This is the most advantage of laser, okay. It's, the laser beam is always 100% straight. Next, that is the, it is by using the laser, it is possible to document the measurement results as PDF, and it can transfer to a PC, okay. And it has the ability to compare the measurement results with ISO standard, which is used for machine tool measurement. And the last advantage is that it is possible to read and follow the alignment from where you are standing and making adjustments. So these are the advantages of lasers. Now let us see the next, the techniques, okay. So the most widely used technique of laser, which is used for inspection and in process gauging, which is known as laser scanning. Okay, so here you can see the laser scanning is there. The laser scanning, it uses a laser beam deflected by a rotating mirror. You can see the HNE laser, that is helium neon laser. Okay, it is deflected by a rotating mirror. First of all, see the different components over here. Okay, let us see further. Okay, so here you can see the different components. Here laser is there. Okay, here rotating mirror, collimating lens, object. Okay, here it is gate over, it is transmitter, and this is receiver. Okay, so here you can see the transmitter here, which is nothing but this collimating lens, rotating meter, HNE laser in this transmitter, and in receiver you can see the collimating collecting lens, photo detector, microprocessor, and digital display. Okay, so let us see. As here a mirror is there, it is nothing but a rotating mirror, and this what it does, it produces a beam of light that sweeps past an object. Okay, that sweeps past an object. Okay, so here you can see the direction of scan is in this direction. Okay, and a photo detector, okay, here the photo detector is there on the far side of the object, senses the light from the beam during its sweep, except for the short time when it is interrupted by the object. When it is interrupted by the object, this time period can be measured quickly with a greater accuracy. Okay, and a microprocessor system, this what it does, it measures the time interruption. Okay, here you can see the laser beam is passes through collimating lens, and it is here on the collecting lens, which is detected by this photo detector. And if the object is kept in between these, then there is a time interruption occurs. Okay, and this interruption is measured by this microprocessor, which is related to the size of the object in the path of the laser system or in the laser beam. Okay, and what it does, it converts from time to linear dimension. Okay, and scanning laser beams can be applied in high production, online inspection, and gauging, and signals can be sent to production equipment to make adjustment in the process or activate a sortation device on the production line. Okay, so what it does here, as you can see, this microprocessor, what it does, it measures the time interruption, and what it does, it relates to the size of the object path of the laser beam and converts from time to linear dimension. Okay, and this system, what it does, it can be applied in high production, online inspection, and gauging, and whatever the signals is there, these signals can be sent to a production equipment to make adjustment in the process if any problem is there or if any defect is there. Okay, so that it send the signal to production equipment to make adjustment while in online inspection and gauging. Okay, at that time this can be used laser scanning measuring system. And the this application of scanning laser system includes rolling mill operation, wire extrusion, machining, and grinding, where this laser scanning measuring system can be used. Where I will repeat for once again: rolling mill operations, wire extrusion, machining, and grinding. Okay, and the non-contact nature of laser scanning makes it well suited to in-process measurement, including such difficult tasks as the inspection of hot rolled or extruded material. And its comparative simplicity has led to the development of highly portable system. Okay, so this is how the laser scanning measuring system can work, and this system can be used for the inspection and gauging system. Okay, so next we are going to see the that is the techniques. This is what the laser scanning measuring system technique. Next, the laser triangulation technique. Okay, so here the triangulation is used to determine the distance of an object from two known locations by means of trigonometric relations of a right triangle. Okay, so here you can see the laser is here. Okay, and here the photo detector is there, and here the part is there. Okay, so the principle can be applied in a dimensional measurement using a laser system. You can see in this diagram. Here you can see the laser beam is focused on the part or the object to form a light spot on the surface. Okay, and a position here, this a position, what it does, this a position, the position of this photo detector, okay, whatever this position is there, the position of this sensitive optical detector is used to determine the location of the spot. Okay, this is used to determine the position of the spot of this laser on this part. Okay, and the angle A of the beam direction at the object and the distance h are fixed and known. Okay, this A and H is known, and this and it is given that the photo detector is located at a fixed distance above this work table, and the part depth D is determined by the formula, that is D is equal to H minus R. Okay, so by using this formula the depth can be calculated. Now how to calculate this R? R can be calculated by this, we know L, so R is nothing but L tan A. Okay, so H minus R, H should be here actually. So H minus R, then we will get the D. Okay, D is equal to H minus R, and R is nothing but L tan A. Okay, so tan A is nothing but R upon, sorry, L upon R. Okay, and R is nothing but L tan A. So D is nothing but, final equation is H minus L tan A. Okay, so in such a way we can find out the depth of this object. Okay, so third one is that the automatic inspection system is there. Okay, here in that system we have seen the two system. First one, that is the laser scanning system. Second one, the laser triangulation. Third one is the automatic inspection system. Okay, in this the automation inspection is achieved, okay, which is integrated into the manufacturing processes. Okay, and in this, if the measurement from the automatic inspection indicates the output of the process is beginning to drift towards the height side of the tolerance, corrections can be initiated in the input parameters by bring out the nominal valve. That means this is fully a automatic inspection system. In this inspection, in this a product or a part is compared with achievable standard, and in the automatic inspection system it involves integration of inspection with production in the same cycle. Okay, so what happens, this could save a material handling, and defects are identified and rectified more quickly, so it saves the material and sources. Okay, and this automatic inspection system depends on number of different technologies including computers, electronics, optics, ultrasonics, photographics. And it is widely used to reduce inspection cost, reduce cost, error rate, and it also shorten the inspection time, avoid inspector monotony. Okay, so this a critical requirement for all automated test equipment is precision instrument, and repeated measurements on same unit of product should yield same result with some applicable range of variation. So this is what the advantage of the automatic inspection system. Now next we are going to see the laser interferometers. Okay, as we know, laser light is monochromatic, coherent, and less divergent. So it is sometimes difficult to extract information from laser fringes closely spaced. Okay, so accurate measurement of distances greater than few was very difficult until the development of laser interferometry. So the resolution obtained can be 0.01 microns. Such equipment is particularly useful for checking the movement of machine tool tables, aligning and checking large assembly jigs, and making measurement of intricate machine parts like tire tread molds. Okay, where these laser interferometers can be used. Here you can see the calibration optical setup is there. Here the calibration of the x-axis linear table displacement is there of a vertical spindle milling machines. Okay, this is one of the optical setup is there. Okay, and the laser interferometer uses a helium neon laser beam which split into beams, and here you can see the next. This is one of the schematic component of a frequency of laser interferometer. So as I was saying that the laser interferometer uses a helium neon laser beam split into two beams, each of different frequency and polarized. When beams are recombined, any relative motion of the optics creates a Doppler shift. Okay, in the frequency. This shift is then converted into a distance measurement. Okay, and the interferometer used for calibrating x-axis linear displacement. Here you can see in such a way. Okay, and the whatever the horizontal straightness is first recorded in a series of say 0.1 movements. Okay, so here this is the schematic component of a laser interferometer. Okay, here you can see this spindle is there, this is the movement of the table, and this is the photodiodes, and here further the Doppler, and here the calculator and display is there. Okay, at the end. Also this laser interferometer, the next diagram we will see. Okay, here you can see that this can be also used for machine tool elements. Okay, for the horizontal straightness and squareness of x and z axes. Okay, now next we are going to see the type of laser interferometer. So this is first one, that is uh, Michelson interferometer. Okay, this is the oldest type of interferometer which has subsequently has been modified in several respects and lot of sophistication introduced. However, this Michelson, using this interferometer, it is established the exact relationship between meter and red wavelengths of cadmium lamp. So the understanding of its working will be of interest to all. So the basic Michelson interferometer consists of a monochromatic light. Okay, here you can see the different components of this Mendelson interferometer. So it consists of a monochromatic light source, a beam splitter, okay, a beam splitter, and mirrors. Okay, and this relies on the principle of constructive and destructive interference. Okay, so this relies on the principle of constructive and destructive interference, or as one mirror remains fixed. So here there are two mirrors are there. One is movable mirror and another one is fixed mirror. Okay, so this relies on the principle of constructive and destructive interference, as mirror remains fixed and other is movable. Okay, so here in this Mendelson interferometer, it utilizes a monochromatic single wavelength light, okay, from an extended source. Okay, and this light falls on this beam splitter. Okay, so in this way you can see the Mendelson interferometer falls on this beam, and again the observer can see the constructive and destructive interference over here. Okay, so next, that is the single. In this we will see the single frequency DC interferometer system. This is what the much improved system, or the Mendelson simple interferometer. It uses a single frequency circular polarized laser beam. Okay, so on reaching the polarizing beam splitter, here you can see beam splitter is there, and here the polarized laser beam is there from laser source. So on reaching the polarized beam splitter, the beam split into two components. Okay, the reflected beam being vertically polarized light, and transmitted polarized light, and the transmitted beam can be polarized light. So these two beams, first is on this polarized light, second one is on this the transmitted beams. Okay, so these two beams is referred as a reference arm and measurement arm. Okay, and they are respectively travel to their retro reflectors and are then reflected back towards the beam splitter. Okay, so what it does, from this laser source, this polarized beam falls on this beam splitter, then again from these retroflectors, the on these reference arms and the measurement arms, it falls and again reflected back and falls on this beam splitter, and again through this detector, this length can be the inspection can be performed over here. Okay, this is what the single frequency DC interferometer. Now next we are going to see the AC interferometer. Okay, so the measuring capacity in interferometers with lamp as a source of light is limited, because it is not possible to maintain the sharpness of interference fringes beyond certain distance due to the size of the lamp. Okay, so the laser interferometers, what it does, it uses AC laser as the light source, and as AC laser as the light source, and it enables the measurements to be made over the longer distance because it is possible to maintain the quality of interference fringes over the long distance when the lamp is replaced by a laser source. Okay, when the lamp is replaced by a laser source. It must be understood that white light emitted by a lamp is a combination of waves at different frequencies, but laser generates a continuous stream of light waves, resulting into high coherence. Laser represents a source of intensely monochromatic optical energy which can be collimated into a directional beam. Also, a laser beam wavelength is exact and pure for highly accurate measurements, and it utilizes the principle of both optical technique and digital electronics, and is highly accurate and versatile measuring system that can cope up with industrial environment. In case of AC laser interferometer, position information is carried as phase deviation rather than as a signal amplitude deviation, thus giving a much improved signal to noise ratio. Okay, so this is what the laser interferometer. Next, that is the application of laser interferometers. As laser interferometers are used in interference measurement where higher accuracy is required, and it is used for checking the movement of machine tool tables. It is also used for aligning and checking purpose of large assemblages. It can be used for intricate machine parts measurements. Okay, so if we see the further the broad area, first that is the life science. In life science, it can be used for a fluorescence microscope, in DNA sequencing. Okay, and next broad area was the in metrology and sensing. It can be used for a spectroscope and in interferometry. Okay, and in industry it can be used in further in micro machining and gas sensing, and in scientific it can be used in holography and dynamic life scale. Okay, so in such a way we have seen the laser interferometer. So today we have covered the laser metrology, the basic concepts of lasers, advantages of lasers, techniques of laser systems. In that we have seen the laser scanning system, laser triangulation, automatic inspection system. Then we have seen the laser interferometers. Okay, and that we have seen the working of its. Then we have seen the types of laser interferometers, that is a Mendelson interferometer. In that we have seen single frequency DC interferometer system, AC interferometer, and last we have seen the applications of laser interferometer. Okay, so today we are going to stop over here. Thank you.